So continuing on with section 3.7 on optimization, we have what point on the graph of f of x equals 5 halves minus x squared is closest to the origin. So another very common optimization problem, it's asking about something being closest. So you're trying to basically minimize distance here, and that's actually what I'll write. So optimization is the type of problem, optimization. And like I said here, we're trying to minimize distance, and that's what tells us it's optimization. So we're talking about a function. You can see the function is graphed here. It's just a parabola upside down with a y-intercept at 2.5. And you're trying to find a point that is on that graph that is also closest to the origin. So, I mean, just by eyeballing it, you might be able to say it's probably going to be somewhere around here. And that's just a guess, but what's important is more the fact that you're trying to get close to the origin, which we know is 0, 0. And then we have some point out here, which is x comma y. But remember, y is just whatever the y values are, and the y values are the function values, and in this case, you know, the function is 5 halves minus x squared. So we can also just write 5 halves minus x squared for the y value, and then that puts us into one variable very quickly, which we do like to be able to do. So minimizing distance, this is going to take you back to, say, like pre-calculus or maybe even algebra, an algebra course where you talked about the distance between 2 points, because that's what we're trying to minimize, distance between 2 points. And that is a formula that comes from the Pythagorean theorem, because you could create a right triangle here. But if you remember it, that's good. You're basically thinking about the vertical distance and the horizontal distance. And so that ends up being x2 minus x1 and y2 minus y1 for any 2 points. So for ours, we just have to think about what we have. And you can see that we have, I mean, the 2 points right there. And so what we're trying to minimize is that distance. So in our case, I'll make it a little bit bigger here, but I'm just going to think about the 2 points that I have there on my graph. And so it's going to be x minus 0, because one x value is x and one x value is 0. And for the other one, it's going to be the 5 halves minus x squared minus 0. And that 0 is really nice, right? Because it makes things look a little bit better when we actually try to do this. So I'll simplify this a little bit here. I'm going to have x squared, because x minus 0 squared, x squared. And then the second piece is, of course, 5 halves minus x squared squared. So you'd be doing 5 halves minus x squared times 5 halves minus x squared. And if you do that out, you get 25 fourths minus, and then you can think about the fact that you're going to have 10 over 2 x squared, because you have 2 of those, and then you'll have a plus x to the 4th. So that's what you have underneath, and I'll even do, you know, one more simplification. So we're going to have basically 2 over 2, so maybe I'll just move stuff around. Maybe that makes it easier for you. And I'll have a minus, looks like, I was going to say 8 over 2, but that's the same as 4. So what I'm doing there in my head, let me talk it out, is if I want to combine my 2x squareds, I'll have to give them a common denominator. So you can see that I'm going to have, this is 2 over 2 and then minus 10 over 2, so that's a negative 8 over 2, or a minus 4x squared, and then we still have that 25 over 4. Okay, so that's our distance that we're trying to minimize. So in thinking about number 5, arguably x could be anything. I mean, there's no value that you can't put in for x and, you know, come out with some number. Now we know that in reality, x is not going to be something very, very large because we're trying to minimize distance, but we don't actually have any restrictions on the x. It could be positive, it could be negative, but it could be anything. So at this point, we now need to take our derivative, and the big thing with these types of problems is to understand that when you're trying to minimize something like this, if I were to take the derivative, I have something to the 1/2. So when I take the derivative, I'm going to end up with that same thing to the negative 1/2, which goes into a denominator. And what sits in the numerator is simply the derivative of the inside. And so we can make our lives easier by just understanding that we really just need to minimize the inside of this. We don't have to think so much about what happens, on the outside with the chain rule. So what I'm saying there is this is this inside here to the 1/2. So the derivative is going to be 1/2 times that inside piece, and this is what's always going to happen, 25/4, to the negative 1/2, and then we're multiplying that by the derivative of the inside, which is 4x cubed minus 8x, and then, really, that's it, because the derivative of 25/4 is not there, it's constant. So what I'm telling you is you can think about this as 4x cubed minus 8x over 2 times the square root of x to the 4th minus 4x squared plus 25/4. But my point of that is, and this is the derivative, but really you're just trying to find out when is this thing equal to 0. So let me just go ahead and do that, because why write more here? We know that we've already taken the derivative. So you're trying to find out when this is equal to 0, which is really just when the numerator is equal to 0, because it's a fraction. And that's always going to be true. Now, if you say, oh, but I can simplify this 2 with this 4, that's fine. And then, of course, it has to happen over here too, that 4. That's no problem. If you want to make your life easier, why not? So you'll have 2x cubed minus 4x, and you want to know when that's going to be equal to 0. So if we factor out a 2x, we have x squared minus 2. When is that equal to 0? And then setting these both equal to 0, we can see that we get x equals 0, and then we get x squared equals 2, or x equals plus or minus square root 2. And so there's a lot there that's happening. And so at this point, what we would do is we would now think about a sign chart to think about what's happening on either side of those values. And just due to wherever my face might be, I'm going to put that up here. So I'm going to have x equals 0, and then I'll have x equals negative root 2, and over here I'll have x equals root 2. Notice the denominator is always going to be positive in this case because it is a square root there, and we just really have to think about our numerator. So if we were to put in values, and I'll just for time's sake, if you were to put in values on either sides of all these, you are going to have negative, positive, negative, positive. If you're putting these into the derivative, just see what happens in the derivative. And so what that's telling you is that you have a local min right here, local min, and then you have a local max at 0, but you don't really care about that because you're not trying to maximize anything. And then you have another local min at the square root of 2. And that's not surprising because this is a parabola, and the parabola has, as you can see, symmetry. So not surprising. Okay, so now we can see that we're going to have some minimums where the points are going to relate to both negative root 2 and root 2. So we just need the y values. And so if you put those in, the y value that comes out, now this is going back, remember, into the original. So if you put the square root of 2 here, just to think about it, if you put the square root of 2 in to your original, you're going to have 5 halves minus 2, because the square root of 2 squared and the negative square root of 2 squared is 2. And so that's going to give you 1/2. So you have the y value of 1/2. So to answer the question, the points closest to the origin are, and we have root 2 1/2 and negative root 2 1/2. And those are the 2 points closest to the origin. And if we look at like where we put our like sample point there, we can see we're probably a little bit off. It probably is a little bit farther down because root 2 is about 1.41. But the point is here that we have 2 points because of the symmetry that are actually the closest. So one more example of optimization. All right, so another kind of quintessential optimization problem here, which is about a window. So an architect wants to draw a rectangle inscribed in a semicircle of radius 8. If one side must be on the semicircle's diameter, what is the area of the largest rectangle that the architect can draw? So very common to try to, like, you're trying to make the largest rectangle, but it's constrained by the semicircle. So remember that idea of constraints is very common. So we're going to optimization. Notice I've said that every time. And area of the largest rectangle. So area of a rectangle. So this is similar to the first one in just that we have an area of a rectangle, but the constraint is very different. So it's a different problem. And so number 3 here is the picture. So we're going to try to, we already kind of have the picture here, so we don't need another one. So length times width is the big idea. We have a semicircle, it has radius 8, so we don't want to forget that we do know this distance from here to here, and that is 8, because that might be an important piece of information for us. And the reason why it's important is mainly because since it's a radius, it's any outer edge to the center. So in that same vein, this value is also 8. And that's really what's important here, because it's going to help us to find the area of the circle. Now, thinking about the rest of this picture and how we can label it, we can think about giving one of the variables x. So you can call them L and W, but I'm going to call something x here. So I'll call this x. And when I call this x, notice that because the radius is 8, I now have a right triangle. And so that tells me that this distance down here is the square root. And thinking about the fact that a squared plus b squared has to equal c squared with the Pythagorean theorem, I'm going to have 8 squared, or 64, minus x squared. That's going to be that distance there. Now, of course, that's important because if I'm thinking about the area of the rectangle, I need length times width. And so it's really important to remember with stuff like this that you're going to have symmetry. And with symmetry comes things that are equal length. So although you don't have to draw it, you want to understand that if you were to think about putting this in half, this is going to be another 64 minus x squared. And now you know the length of your rectangle, and you also know the width of your rectangle, or height of your rectangle, however you want to call it. Now in terms of x, it should really be, it needs to be greater than 0 because it's, creating this rectangle. But we can see from the fact that we have a square root idea that it can't be any greater than 8, because it could never be greater than the radius of the circle, because then it would be outside of the circle. That doesn't make any sense. So I'll actually do some of the work. I have 4 and 6 down here, but just due to space, let me kind of bring them up here. So for our rectangle, we have area, which is going to be x times, and then I'm going to need to take this length plus this length, and I'm just going to add them together, so I'll get 2 of them. They're like terms. 64 minus x squared. So that's the area of that rectangle, and we're trying to maximize it. We're trying to find what is the largest area. The constraints are the fact that since the radius is 8, it constrains that bottom distance. That's why it can't be any bigger than 8 for x. And so now that we have this, I can, if I want, write it as 2x square root 64 minus x squared. And then now I'm going to try to, I need to take its derivative because I need to maximize or minimize, thinking about local mins, local maxes. That comes from when the derivative is 0. So I'm going to use the product rule here. And so I'll take the derivative, I'll look at it like this is one piece and this is my second piece on the product rule. So the derivative of the first is 2. The second is just 64 minus x squared. And then the first times the derivative of the second is going to give us 1/2 times 64 minus x squared to the negative 1/2 times the derivative of that, which is a negative 2x. So now, once we rewrite that, I'll have 2 square root 64 minus x squared. And then this second piece, one of the two simplifies with this 1/2, so I have a negative 2x squared over, and then that square root of 64 minus x squared. And then what I want to do is combine them so that they have the common denominator of the square root of 64 minus x squared. So that means multiplying the first piece top and bottom, so I have to give it a bottom. And that's going to get rid of the square root. And then in my denominator, I'll have the square root, 64 minus x squared. And then in the numerator, just the negative 2x squared. So you should be able to see, hopefully now, that that's going to give us 128 minus 4x squared over the square root of 64 minus x squared. And just like always, we just need that numerator to be equal to 0. That implies, when is the numerator equal to 0? Which, if we bring the 128 to both sides and divide, which I'm doing just due to space issues here, we get x squared equals 32. So therefore, x equals the square root of 32, plus or minus, but we can't have the negative because we have our restrictions on x. So x equals the square root of 32. And, you know, that's going to be 4 root 2 if you simplify it, and which is some number. Again, the answer just wants the largest rectangle, so I might not make that into a decimal if something comes out nice. So x equaling the square 4 root 2, that means that that would be this here. Now if I want the bottom, I need to essentially, let me just think about the length here. That's going to be the square root of 64 minus, and then x squared, so that would be 32. So that's going to be, and I should put a 2 on this if I want the full length of the rectangle, because there's 2 of them. So that's going to be 2 root 32. And which would be like 8 root 2. But here's my point. We can, put our x on here. We can put x equals 4 root 2, check it in the derivative of our area. And if we put it in, let me just look here, what derivative would be best? Well, denominator is always going to be positive. So if I think about values on either side and put them over here, if I put in, 4 root 2 is, not that big. So I put in something less than that. So say I put in 2 squared times 4, 128 minus that is going to be a positive number. If I put in something big like 10, if I square 10 and get 100, multiply it by 4, that's 400, so that's going to give me a negative. So that is in fact telling me that I'm maximizing things, that this is a local max for the area. And so that's what's telling me that I'm creating the largest rectangle. Now, the question actually asks, I'll bring it over here. The question asks, what is the area of the largest rectangle? So area is going to be x times y. X is, well, y being the length, 4 root 2 times 2 root 32. I did that kind of weird, but the point is you get basically 8 times the square root of 64, which is 8, so you get 8 times 8. So you get 64. So the area of the largest rectangle, so the area of the largest rectangle is, and we'll say 64 units squared, simply since it doesn't tell us any kind of units here, it just says radius 8, so we can use units squared to indicate that that's area, and we've answered our question. So that is, you know, what we were trying to do there, area of the rectangle. So we found largest, we were maximizing the area of the rectangle. Okay, so those are all kind of like 4 different examples of optimization problems. Notice each one's a little bit different, but they follow the same kind of rules. The only other place you might see these, this would be more if you were to take business calculus, so we don't see this quite as much, but whenever you see RX, PX, CX, those things are profit, cost, revenue, and it's not uncommon to maximize or minimize them, which is why we talk about it here real quick. But if you are asked to maximize revenue, revenue is X times little p of X. X is units sold, and P of X is price per unit. And if you're thinking of maximizing profit, because you'd want to maximize it, not minimize it, R of X is revenue, and that's in terms of units sold, and C of X is cost. And these are functions, so revenue function and cost function. So you just have to remember, the reason I bring it up is because you have to know this piece of information here to create the revenue function, and you need to know this right here in order to create the profit function. So understand that you may need to use this to create the revenue function and then subtract it from the cost function to get your profit function, which you can then take the derivative of and maximize your profit.